Hi, it's me, Andy. We don't know you. That doesn't matter. What does matter is I'm here to explain something to you. We'd prefer if you didn't. And I don't care what you prefer. You know what I do care about, though? Hawking radiation. This is an English class.
I don't care if this is an English class, you did physics!
Alright, let's do this. Hawking radiation was first proposed in the year 1974 by scientist Stephen Hawking. In simplest terms, Hawking radiation is radiation emitted by a black hole. But that's impossible. Why? A black hole's gravity is so powerful that not even light can escape. If its gravity is so strong, how can it emit anything? That's exactly what I'm here to tell you. First, we need to understand three base concepts. We need to understand the event horizon, particles versus antiparticles, and finally virtual particles. So let's start. The event horizon is a point of no return for the black hole. Once you cross it, you can't go back. Think of it like a door that only opens on one side. Once you go in, you can't come out. Next, we talk about particles and antiparticles. This is our particle. This is his antiparticle. They're both exactly the same. Same mass, same everything, except for one key difference. One is positive and one is negative. As a result, when the two collide, they annihilate. Next, we need to talk about virtual particles. All around us, there are particles, but there's also something we call a virtual particle. This is best described as a particle that doesn't exist yet. It's a quantum fluctuation that has some properties of a particle, but it's not quite there yet. If these particles are allowed to exist for long enough, they can become real particles, but the problem is that there's also virtual antiparticles. These virtual particles and virtual antiparticles annihilate each other, so neither one can become real. Alright, now we can finally talk about why Hawking radiation happens. Now let's quickly review. Get on with it! What? You're gonna go over your time limit! Alright, so we're at the black hole. We're at its event horizon. We have a particle and we have an antiparticle, but they're not real yet, they're virtual. Finally, they're on two opposite sides of the event horizon. We're gonna let them collide and see what happens. Boo! What are you doing? You said they would annihilate each other. I came here to see some action, and I saw none. My disappointment is immeasurable, and my day is ruined. Do you want to know why they're going to annihilate each other? Not really, no. Well, too bad on it. They can't annihilate each other because they're on opposite sides of the event horizon. The event horizon has split the pair. The virtual antiparticle is drawn into the black hole, but the virtual regular particle is shot out into the cosmos and exists long enough to become a real particle. That is Hawking radiation. Well, sir, that was a lovely lesson, but I don't care. But wait, there's more! Hawking radiation has an extremely important effect on the black hole. The energy used by the virtual particles to escape the black hole comes from the black hole itself, and according to the equation E equals mc squared, energy and mass are related, so as energy is used for the particles to escape, the black hole loses mass. We call this phenomena black hole evaporation because the black hole was literally evaporating as the Hawking radiation is emitted. Would you look at the time? I got places to go, people to see, so now I guess it's best to take my leave. Thank you all for listening. Have a nice day.